Hi, everyone. So I'm Will Mao. I'm a postdoc in Denise Cai's lab. I'm going to let Joe and Zach introduce themselves.
Hey everyone, I'm Zach Pennington, also a postdoc in Denise Cai's lab.
Joe, are you here?
Hello, can you guys hear me? Okay. Hi, I'm a fourth-year PhD student in Denise Cai and Kanagarajan's labs.
Cool. And so we're all experimentalists, and we're going to try to share with you guys our tips and tricks and generally, practically speaking, how to get Miniscopes working and your animals behaving. So I have been working with Inscopic scopes for 4 years, and then I recently started working with the UCLA Miniscopes for the past 2.5 years. So we're going to share with you guys what we think are the best practices and how to get your experiments off the ground. Again, I encourage everyone to ask questions in the chat, and we'll answer them best we can. We're also in the process of writing up a Google Doc to share with you guys after the workshop that'll contain all of this information and more, so no need to take any notes. So I'm going to hand this off to Joe.
Okay. Can you do one animation? Thanks. Okay, so now we have separately prepared a Miniscope system with Federico and Daniel, and we've also prepped mice with Tristan and Susie. And so we've covered now weeks 1 through 4. So can you do one more animation? So we are here. And so now what we're going to cover are the handling, habituation, and preparation that's necessary to start an experiment using Miniscopes. And we're curious to know at what stage you guys are at in running Miniscope experiments. So we've launched a poll. Okay. Okay, the answers are coming in.
It's starting to look like a lot of you guys are in the pre-surgery planning phase of the experiment. Some of you are collecting data. I'm going to stop the poll in a few seconds. Yeah, so it looks like about 60% of you, oh, I got an error. Well, it looks like about 60% of you are on the pre-surgery / planning phase. 22% of you are actively collecting data. 10% of you have finished collecting data or currently analyzing data, and 10 of you have done all of the above. So yeah, so we'll get into a lot of the steps that you need to do to actually fulfill to get your experiments all planned and get your animals behaving. So this will apply to a lot of you. Okay, so the first thing we want to do when we're starting out with attaching these scopes to animals is to actually handle them for a little bit. So one way where you could do this is just to take a mouse out of its cage, place them in your hand for about 1 to 2 minutes each day, just to get them used to human touch, the sounds that they might encounter during experiments, and so on. So this is a mouse that's been well handled, and generally we'll do this about 2 to 3 times before you actually start messing around with their base plate and stuff. But this will vary depending on the types of behaviors that you're doing. But generally, you want to spend at least a little bit of time with each animal, letting them get used to you.
Okay, so once the mice are well habituated to you, now you have to get them used to the process of putting on and taking off the Miniscope. So over here, you see I just removed the base plate cap and with the screwdriver and then put on the Miniscope. And there are many ways that you can do this. I like to keep the mouse on the top of their cage because they tend to hold on to the gratings of the cage, which makes it very stable. And there are a few things that I want to point out. So one thing you'll notice here is the way I'm holding the screwdriver is with my palm down, which makes it parallel to the mouse, as opposed to if you held it at an angle, you're kind of propping the head of the animal, which would put the mouse's head in a very awkward and uncomfortable position. So you really want to make sure to not make the mouse uncomfortable to the extent that you can. Another important note is that if early on the mouse seems too stressed and struggles when you try to do this, I think rather than to persist, it would be better to stop trying, have the mouse calm down some, and then try again, either during the same session or a subsequent session when they're more habituated to you. Oh, and one last note is that, so you'll notice here that I have the Miniscope propped right next to the mouse, and I know exactly the orientation that it's in. And I do this very specifically so that once the cap is out and the screwdriver is holding the mouse, I can very quickly grab the Miniscope and I don't have to turn it around to find the orientation that it needs to go in. This allows you to make this a smoother, faster thing.
Okay, so then once you've attached the scope, the next thing you want to do is change the exposure and the focus of your scope. So for this mouse, we already figured out the correct focus. And so as Daniel mentioned, we had set in the configuration file the optimal electrowetting lens focus and the brightness of the LED to get our optimal image. But in the hardware, or in the software, you can change the focus as you wish. So this is just an image, a screen grab of us changing the electrowetting lens focus in real time in the image that you see. And generally, when you're looking for the perfect image, you want to be able to see sort of the centermost cells appear most smallest and have them really crisp. The reason being that the cells mostly in the center are the ones that will be that will have the less distortion due to the lens. Once you have a lot of those cells that are in focus, then you can remember which what setting you have for your focus, and then save that into your configuration file so that every time you open up that file, you'll get the same focus. And same with the brightness.
So we want to habituate the mice to the weight of the scope for an extended period of time so that when we start the experiment, the weight of the Miniscope isn't too heavy and won't affect the animal's behavior. And so what we like to do is put the Miniscope on the mouse's head and have them explore, in this case, in their home cage for 5 to 10 minutes a day. This is what I tend to do 5 to 10 minutes a day because the arenas that my mice explore tend to not be much larger than this arena. But for example, if your experiment demands a mouse to run along a linear track, you might prefer to have them habituate for longer periods, say 30 minutes a day, as they're performing the behavior.
Okay, so once you've habituated the mice to the scope, or after you've run your experiment, you can then remove the scope, and that's just as simple as attaching the scope. Again, you use your dominant hand to wield the screwdriver, use that screwdriver to sort of hold the mouse's head still with the screwdriver still in the screw. Then you can unscrew, take off the scope, and put the base plate, the base plate cover back on.
And so here we just aggregated some behavioral videos from the lab of experiments that we've run with Miniscopes recording across different behaviors. And so, for example, we have mice on a elevated plus maze, linear track or circular track or open field. So these top four, which are they're typically bigger arenas that have mice exploring larger fields of view. Linear, circular, and open linear track, circular track, and open fields are often tasks related to spatial navigation. So here we could see that animals are capable of freely moving despite the tether. And then in the bottom, some other behaviors on the left, so context learning or fear conditioning or light dark box. And then in the bottom right, which are some things that people have been asking about today, which are the capacity to which we can record for very long periods, say chronically. So all the way in the bottom right, we have a mouse that's living in a custom-made home cage that we've designed, where the mouse lives with a Miniscope on for, in this case, up to 2 to 3 weeks. And this requires us to use a commutator, which you can kind of see at the top of that video. And yeah, this mouse is able to live with this on for very long periods of time.
Okay, so now we'll go on to some frequently asked questions. Some of these questions I've already encountered in the chat from previous sessions. The first one that I'll talk about is how do you trigger Miniscope acquisition from an external source? So in some experiments, you might want to use a TTL pulse to initiate recording of the Miniscope and the behavior camera, but also of some kind of stimulus protocol that you might need. So for example, I have an Arduino setup where I begin acquisition of imaging as well as starting the behavioral protocol that is allowing the mice to lick at specific water ports and acquiring timestamped licks and so on. So for older versions of the DAC boxes, what you can do is open up the box and solder signal wires to these signal and ground pads here, and then simply connect them to your external source, have your external source send a 3.3 voltage signal that can begin acquisition. But newer generations of the DAC box come with this SMA port that's already been built in here. So all you have to do is plug in an SMA connector that is linked to your external source and have your external source send the signal to begin acquisition. And this will trigger both the Miniscope acquisition and the behavioral camera acquisition together if you have those. And on the software side, all you need to do is turn on the triggerable option that's at the top left corner of the software. And then the bottom left should look something like this, where it says external trigger enabled. And then what it's going to do is simply wait for a signal from your external source, and it'll begin acquisitions once that signal is detected.
So this is something that we've covered somewhat already, but if you just put the Miniscope on the mouse and you're trying to find the optimal field of view, what are the landmarks that we're looking for to find the optimal set of settings? So over here we have two fields of view, neither of which is optimal. On the left side, you can see that the vasculature is barely distinguishable and the cells don't peek out above the background. Whereas on the right side, the LED is too high, and although you can make out the vasculature and a lot of the cells, the whole center field is oversaturated. And importantly, what you can, let me see if I can annotate this. So, whoops, one thing to note is the only thing different between these two is the LED that these two are set at. So on the left, they're too low at 6, and on the right it's too high at 46. And so, Will, if you go to the next slide, then now this is an optimal field of view where both the vasculature and the cells are well exposed. And this, now you see the LED is somewhere in the middle at 17.
So,
Sorry, go ahead. That was it.
So here, a lot of you have asked, how do you reliably capture the same field of view across sessions? The answer is that when you screw the scope in, it's been mentioned that the set screw is conical, so it sets into the sleeve of the Miniscope in such a way that the X, Y, and Z planes are all aligned. But sometimes if you don't screw it in tight enough, or if you screw it in way too tight, then you could get instances where the field of view might look shifted. And the way to counteract this is to just take a screenshot of your field of view every time you're about to image and compare it to a reference where you know you have the optimal focal plane. And we advise you to do this rather than doing it from memory, because people do make mistakes when they're trying to remember what the field of view looks like. So I say simply take a screenshot, save it somewhere, and just compare your current field of view to that screenshot every time you image. So here is a little quiz. I'll launch a poll. So which of these do you think is from a poorly attached Miniscope? The majority of you are answering correctly. I'm going to end the poll here. And the correct answer is A, because all the cells are out of focus, and the image from A look very different from the images in B and C. So again, while it might look like you can see sort of vasculature here, that vascular is highly out of focus, and with the visual assistance of these screenshots, you can clearly see that they are not in the same field of view. So what has probably happened here is you've probably screwed the Miniscope on too tightly, or the attachment was slightly off, or it was too loose. So when this happens, and it's very rare that this happens, I had to deliberately do this, deliberately attach the Miniscope poorly to get this field of view. But when this does happen, usually detaching the scope from the base plate and reattaching it will fix this problem. However, there could be cases where the field of view has truly shifted, perhaps due to maybe growth from underneath your implant that has shifted the field of view, in which case you may need to change the electrowetting lens focus as a last resort.
Okay, so there are a lot of instances where you might be doing an experiment where the animal is turning around in many, many circles in one direction. Well, first, I guess, all right, people are already answering the poll, but alongside this, so people might be running experiments where animals are running around in circles for an extended period of time. And with a standard coaxial cable, this could allow the wire to tangle. And if it tangles and kinks too much, this could compromise the connection from the Miniscope to the DAC to the computer, which could result in dropped frames or a disconnection. And so one way to counteract this is to use a commutator. And so over here on the left, we have the parts that you would need to assemble a connection from the computer to the commutator. So the USB cable and DAC are the same as before, But now instead of directly connecting the Miniscope to the DAC, you have this male-to-male SMA connector that connects the DAC to the commutator, and then the commutator gets connected to the Miniscope. And so now if the animal is turning in one direction for an extended period, the wire should never tangle. And so now on the right, you see it fully assembled, what it would look like.
And we have a bunch of vendors that we've worked with that have made commutators for us. We've mentioned Dragonfly. There's also Neurotech, which is the one that we have shown in this image here. We'll put up all the information for what kind of vendors that we've worked with on this Google Doc that I mentioned at the beginning that we'll plan to share with you after the talk.
And the last bit is that even sometimes while using commutators, it's possible that the torque required to engage the commutator, while still low enough for the animal to turn, sometimes it can still cause a twist in the coax cable. And oftentimes this happens near the base of the Miniscope, near the head of the animal. And so one way to counteract this is right at the base of this coaxial cable where the micro FL connector is, you can secure the cable using Coaxial with the blue arrow, and then a piece of tape, in this case red tape designated by the black arrow. And so essentially what this does is creates rigidity in the coaxial cable, and this will transfer the torque up to the commutator to engage the commutator without twisting or kinking the coaxial cable. So we found that this is very useful for preventing twists and tangles.
Okay, and then the last thing that we want to talk about is how to align your imaging, your calcium imaging with the behavior, because that is a lot of, this will be a very common thing that experimentalists will need to do if they're acquiring both imaging and behavioral data. So as Daniel mentioned, the Miniscope acquisition software will save timestamp CSV files that'll have the millisecond timestamp of each frame for both the Miniscope and the behavioral camera. In general, the frame-to-frame, I guess, matching frame to frame, the Miniscope and behavior cameras will be relatively close, but they won't be perfect. And especially if you have different frame rates for both the Miniscope and the behavioral camera, those frames will not match up. So what you can do is simply read the CSV file and find the closest matching frames for your Miniscope timestamps that appear in your behavioral timestamps. And we have some sort of in-house code that we can share that will do this, but it's highly encouraged that you sort of do this yourself because experiments can differ a lot on a case-by-case basis, and you will want something very specific to the case that you're dealing with. So we have some guidelines that I have in my personal repository that you can look at. But in general, this is something you probably would want to code up yourself. And then with that, that's all we have for the FAQs, and I'm going to hand it off now to Zach, who's going to talk about tracking behavior.
Well, and if you could unshare and I'll reshare on my end.
Oh, yeah, that works.
Okay. All right. Hi, everyone. Again, I'm Zach Pennington. I'm a postdoc in Denise Cai's lab. In addition to being a Miniscope user, I'm also a developer of the behavioral tracking software EasyTrack. And I'm going to talk a bit about how we go about syncing our Miniscope recordings with behavior. First, introducing kind of the range of open source behavioral tracking software that are out there and some considerations that you can make when deciding which software is the best option for you. And then I'll give a quick tutorial on how to use the software EasyTrack, which we developed really chiefly to surmount some of the hurdles in tracking behavior of animals wearing Miniscopes. Okay, so there are two kind of broad classes of open source behavior software. One is sort of position-based, and these are really focused on defining the central position of an animal on a frame-by-frame basis throughout your recording. And these are great for a lot of different tasks, whether it's condition place preference, light, dark, circle track, linear track, all sorts of things. And the benefits of these sorts of strategies is that they're really simple to implement. They don't require any model training. They can be executed on just about any computer, which is really great. You know, but they don't necessarily address all of our needs, especially as people look to analyze more and more sophisticated behaviors. And so for this, people are oftentimes using things like Deep Lab Cut, which look to do pose estimation, where instead of just tracking the central position of an animal, you're really trying to identify specific features of the body of that animal and its interrelationship. And so people often use Deep Lab Cut to do this sort of pose estimation. And then there are other software that work on top of Deep Lab Cut to try and define things like grooming or something more sophisticated. And these software, if you have a question that is that needs this information, it's really great. The downside, of course, is that these are a bit harder to implement. They do require model training and can require sophisticated computer resources. So I think it's a trade-off between complexity of the answer that these things provide you and how you go about implementing them. So, if all you really need is the position of your animal in the field of view, I would definitely go with something like this. If you're looking for a more nuanced behavior, I definitely check out Deep Lab Cut or some of these other deep learning algorithms. And these and many more software are available or viewable on the Open Behavior website. This is a great resource just to check out and see all the open source tools that are available to you, both in terms of behavioral apparatus, behavioral measurement, data analysis, neuromodulation. So a lot of cool open source tools. There are just a few that I use, but there are a ton that are up there, and it's definitely worth checking out to see if there's something that fits your research. Okay, so I'll now talk a bit about EasyTrack, which is what we use in lab to analyze the behavior of animals that are undergoing Miniscope recordings, but also just like as a general free behavioral measurement tool that we use in lab. And EasyTrack has two modules. One is for the positional tracking or location tracking of an animal, so just defining its central position within a field of view, and this works on a ton of different types of behavioral tasks. You can also do things like define regions of interest in the field of view, and there's lots of nice outputs that it gives you. The other module that EasyTrack has is designed specifically for the analysis of defensive freezing, which are common to studies of learning and memory. So it just tells you, is the animal active or is it freezing? How much is it moving? This sort of thing. And EasyTrack has a few key capabilities that really make it amenable to Miniscope recording. One is that it possesses wire removal algorithms. So you can either crop the wire out, or there's actually a morphological operation that removes the wire. There are extensive data visualizations. EasyTrack provides both frame-by-frame output so that you can then align your frame-by-frame data with your Miniscope imaging data, as well as bin summary reports. So if you just want to know, how much is the animal freezing in this period of time, or how much time does it spend in this side of the chamber, et cetera. Again, you can define regions of interest. You can crop images. You can define regions that you'd like to ignore. And this is all operating system and hardware independent, which is also really nice. So just a flexible open source tool. And if you want information about how to do this, this is all up on the Cai Labs GitHub account. And there are a couple of manuscripts describing the validation of EasyTrack, as well as a step-by-step guide. The other thing is that this is continually under development. So there are beta test versions of some features that are available. So we have real-time tracking up and running, and there's currently a lab member in our lab who's using the real-time tracking, and then you can sync that up with outputs. So if you want to trigger some sort of output based upon where the animal is, you can now start to do that. And we also have orientation tracking up and running. So in addition to just knowing the central position of the animal, you can now know which direction the animal is facing. And this is helpful for things like place cell studies, where you're going, where you find that place cells are directionally specific. So with that, I'm now going to just give you a brief walkthrough of EasyTrack and what it sort of looks like and how simple it is to get going. Let me share a different screen now. Okay. All right, so this is the part of the location tracking module for EasyTrack, in which you can process a single individual video file. EasyTrack also has batch processing features, but just to hone in on the parameters, it's better to start with individual tracking. And I'll just walk you through this very quickly. I'm going to skip over some things that are less relevant. But this is all executed in Jupyter Notebook, where you have a single page that is, you have instructions, code, and outputs all interlaced into a single file. And importantly, the user has to modify very little code. So like most of it is on the back end, which is you can modify if you want, but you don't necessarily have to, or you don't have to at all. So when running this, we can just, for instance, like load our packages. Here, I'm going to specify my directory and the file that I'm going to be processing. Here, I'm just showing you a example file that comes with EasyTrack. So this is set up as soon as you download it. You can define regions of interest, the names of them here. If you want to downsample, you can specify that to speed up the processing. Once we've done that, we can go ahead and load our video. And the first frame will be presented, and we can immediately go ahead and, if we want to, like, for instance, crop the frame, say, okay, I don't want to deal with any of the things outside of this, I can go ahead and select that. And now on all subsequent frames, the video will be cropped to that region. You can also do things like select regions that you would like to be ignored. And it's as simple as just double clicking and drawing a region like this. So let's say maybe the experimenter had to walk into this portion of the field of view, and that might bias tracking under some circumstances. And we'll just draw that. And now those parts of the field of view will be not paid attention to. I'll quickly define a reference frame. So each frame is compared to a reference frame that doesn't have the animal in it. And so EasyTrack will generate this for you from a video that has the animal in it. So you don't have to provide a separate video. You can just provide this, and here's a frame of the video without the animal. All right, and now we'll go down. We can select regions of interest just by running this. And then it tells me, okay, draw regions left, right, top, and bottom. And I can go ahead and do that. And now, when I do my output, Oh, I misdrew that, but I'm going to keep going and just pretend I didn't do that. And because I don't want to draw those again. But the idea is that now for every frame, I'll know whether the animal is in any of those regions of interest. EasyTrack by default does everything in pixel units, but we can provide some sort of scale to be converted. So if I know two parts of my field of view that are a known distance, I can select them. This tells me how far they are apart in pixel units, and then I can supply some sort of scale. So let's say I know that these are 100 centimeters apart. I'll define that, and now all of EasyTrack's outputs will be converted to centimeters for me. I'm now going to set some parameters for tracking. I'm not going to go through all of them, but they're all described in the notebook, which makes it easy. And then I can test these parameters on a subset of frames. And so here are some frames, and I'm going, oh, this isn't looking too great. You know, my tracking is a bit off of the animal. And then when I look at what EasyTrack is paying attention to, I see that, oh, this wire is really biasing things. And so I can go back up to my parameters, and I can see that this remove wire algorithm is set to false. So I'm going to turn it on by just setting it to true. And then I'll redo this and see how things go. And all right, now my tracking looks a lot better. It's on the animal. And so I'm happy with how this subset of frames looks. So I can go ahead and process the entire session. And so we're going through 1,000 frames. This is just on my laptop that I'm running it right now. You can see it's pretty quick. And at the end of this, what we're going to get is a pandas data frame, which gives you frame by frame information. This is also being saved to a CSV file. So the first couple columns are just the parameters that we used. And then I have the X and Y position of the animal on the frame in pixel units. Then we have Boolean arrays for each of my regions of interest, defining whether the animal is in that. So we know that for the first 5 frames, the animal's in the bottom region of interest. I also have a sort of string array of what region of interest the animal is in, whether the animal has transitioned from one region of interest to another, and then the distance it's traveled in both pixels and centimeters. So I have this now. EasyTrack also gives you some outputs that you can look at to see how tracking did. So here I can see the reference frame with a trace of the animal on it. So I wouldn't expect, for instance, for the animal to be off of in this region or this region. So that's looking good. I also get a heat map of that, the relative location of the animal, as well as a plot of the distance the animal moves across the session. Now, when that's all done, I can select and do some bend analysis. So if I wanted to say, okay, how much is the proportion of time the animal is spending in the like first 200 frames, the second 200 frames, and the last two or the third 200 frames, as well as the total distance it's traveled, I can do that. So here I can see, okay, in the first 200 frames, the animal spent 95% of the time in the bottom. It then shifts in the second 200 frames to spending only 30% of time there. And I get the cumulative distance traveled in each of these time bands. And lastly, if we want to see a visual of where the animal is, I can play a portion of the video back by running this, and I can see, okay, how's my tracking look? And that all looks pretty good. So, you know, that's EasyTrack in a nutshell. There are the different modules again. So there's the module for location tracking. There's also this freeze analysis module, both of which have batch processing features and features for removing wires. And there are new features constantly being implemented that you can check out on our GitHub page, as well as our software for calcium imaging analysis. And I'll just say lastly, oh, great. Wanted to say thank you to all the people that made this possible. Everyone in the Cai lab, particularly Phil Dong, who helped develop EasyTrack, as well as there were a number of undergraduates who wrote the papers, and then Will and Joe, who helped put on this presentation. So thank you all for listening, and we can open it up for questions in the last 15 minutes. If anyone has questions, either for in terms of behavior acquisition or EasyTrack. Okay, Thomas, you want to? Oh, Thomas, you're muted.
Do you hear me now?
Yeah.
Sorry, I'm in lab. I need to wear a mask. Thanks for the presentation. Really interesting. I have a general question. How sophisticated are these tracking softwares for freely behaving animals? So I understand. So they get the location and maybe the orientation, but is there also something more when they, for example, interact with another individual? How can they track different behaviors or so?
So I think for those more nuanced behaviors, you'll want to look into some of the deep learning algorithms, like deep lab cuts that have been built on top of it.
Okay, cool. Thanks.
Someone asked if there's a link to the Communicator you guys showed, if it's currently already available.
Yeah, so we're still in the process of preparing that Google Doc that'll have a list of vendors that we use. But I will post in the chat a few, a sneak peek of that, I guess.
There's another question in the chat from Anna that says, when imaging through cranial windows, sometimes they cannot tell if cells are firing. Is this because of titration of virus, or could it be that something, or is that something you can't tell by eye? I can speak to this quickly. Oftentimes in cortex, there's very, very little activity if the animal is anesthetized. So what a lot of groups do when trying to image in cortex, especially when trying to base plate and find kind of the best field of view, is to head bar the animal and not anesthetize them. And so you can actually see some neural dynamics while actively base plating, but it requires you to add a head bar to the animal. But this is very common across a lot of cortical regions. And then the moment they wake up and are moving around, all of a sudden the whole brain region lights up.
The other thing I'll add to that is that for some regions, and with some versions of GCamp, it's a bit more difficult to see fluctuations in real time. So for instance, I was using GCamp M with in the BLA, and I couldn't see anything in the raw video, but then when I used the V4's new delta F over F, I could see dynamic fluctuations. It's just that the range of fluctuation is a bit small. So, oftentimes I would definitely recommend checking with either that, or I think after some pre-processing, when you subtract background, after you've acquired your video, like in Minion, we can do this. It's much easier to see fluctuations And it might just be due to high background. I mean, other people I know have actually just had issues where the even after titrating, their cells just don't fluctuate in activity much. Although, I mean, if you're measuring, looking at pyramidal cells in the cortex, they should definitely be firing, and you should be able to see fluctuation.
So also touching on that, I mean, it's definitely a skill to, as you use Miniscopes, to be able to visually see activity that if you're less experienced, you just think nothing's happening. And there's a lot of data sets that have been sent to me with someone really disappointed that things didn't work, even in my own lab. And then we load it up and it's like, oh no, you have like 20 cells flashing over here. And it can be difficult initially to get a feel for what that looks like. A really good tip is, you can try the delta F over F view in real time, but just playing back a recording quickly helps a lot. So the dynamics can be relatively slow. And if you just kind of load it up in ImageJ and scroll through the video quickly, that will very much help. Very small dynamics visually pop out to you when you're looking. That's There's a question about EasyTrack. In EasyTrack, when you draw the ROIs, are you able to have overlapping ROIs? For
Yes,
example,
you can have,
center
yeah,
versus edge.
You can have multiple overlapping ROIs.
Let's see. There's a couple of questions about commutators, and depending whatever commutator you end up using, some that are designed kind of for Miniscopes will end up having kind of a coax connector on both ends, SMA connector. But if you modify other commutators, like a Dragonfly commutator, I think now they sell one with SMA connectors. But generally, whatever commutator you're using, you want to make the length of cable that's coming out of either end as short as possible before it goes into a coaxial cable connector. So you sort of want to minimize the length of cable the signal has to run through that isn't purely a 50 ohm coax.
So someone's asking, the live delta F over F will be affected by motion artifacts. Are there plans to involve motion correction in the software?
So yes, it's actually, I think, already written into the software, but it didn't seem needed too much. But I don't think it can be enabled by users. Right now, it takes a window of like 30 seconds or so as calculating the baseline fluorescence, and it doesn't correct for motion. It's something we will, I guess, enable in the future, but the goal isn't for the delta F, live delta F over F view to be used for like actual data processing, right? It's just sort of there to give you a feel for, especially when you have very small dynamics, give you a feel for what's maybe happening. And at least in our hands so far, it hasn't needed motion correction, but it should be turned on. It's already written there. There's a couple questions now. Drago, can you unmute yourself?
Okay, so can you?
Oh, wait.
Sorry, go for it, Drago. Please.
Sorry. Well, thanks y'all for all the presentations and stuff. And I think this question will go in this section. So I'm wondering about the wireless V3, right? So I'm working with a behavior that involves a lot of movement and stuff, and it's definitely not a linear track. So I'm concerned a bit about detecting the being able to reliably detect that flash on, because I've been doing wired Miniscope and it's all good, but I'd like to move to wireless ideally. And then is there any way, is it more or less straightforward? I mean, I know the software is open source, but more or less straightforward to say customize the pulsing of this LED to either on a frame by frame basis, or for example set a 2-second slow square pulse, right, that then I can find in my software and then let's go.
That's all possible. The simplest solution, which is the hardware is on the version 3 wire-free Miniscope, and we never finished writing the firmware, even though it's just a few lines of code. It has an infrared receiver that you can send digital commands over infrared to the wire-free Miniscope. to like trigger it to record or to stop recording or pausing. And we just never implemented it. It's on another wire-free version of the Miniscope, which we just put a large Miniscope that we just put up on bioRxiv, and it works great. And we're just now finishing the version 4 wire-free Miniscope that also has it on it, and it will be implemented natively in the system. But you could, as you said, like you could go in and modify the firmware to do other things, like turn on and off the LED at certain times. But kind of the more convenient way would be to be able to just do this all with external triggering over IR, and it's theoretically possible, but hasn't been implemented in that version.
Phil, you have a question?
Yes. Hi, can you hear me? You can hear me. So it's a question about the EasyTrack. It looks great. Thanks a lot for sharing it with the community. I'm wondering the batch processing, because obviously the Miniscope produces many different files of 1,000 frames or however many you specify over the course of the session. If you analyze those as a batch, would you get the output per file, per video file, or can you kind of can you tell the algorithm that it's analyzing the same animal over many videos, or how will that work?
Yeah. No, that's a good question. Currently, no, we typically in our lab actually concatenate the files manually before passing it to EasyTrack.
Okay, yeah, that makes sense. Okay, thanks. That was my question. Thank you.
I can add that the newer version of the Miniscope software, the one we looked at a little bit ago, you can, in the user config file, define the length of a single video file. So if you didn't want to have the files broken up per 1,000 frames, you just set that number really big and just record into a single file, which was at some point implemented because some computers and pipelines had issues with large single data files, but that's nowadays not too much of an issue. So you could basically get rid of that by changing a parameter in the user config file.
Daniel, I actually have a follow-up question for that. So if you were to do that, and let's say your Miniscope crashes mid-session, is the saving being done continuously, or is it only being sort of dumped at?
Yeah, so there's for every video stream so each acquisition video stream runs on its own parallel process, own thread, and it has its own buffer that fills up frames as frames are coming into that video stream. And then there's a separate thread that's just responsible for writing data. And all it's doing is it's constantly looking at all these buffers from the different devices. And whenever there's something that hasn't been written to the drive yet, it will write it. So it's effectively, unless things get really slowed, it should be within, the buffer should really not fill up more than a frame or two before it gets written. So if things crash, the data is stored. There is a rare case in which the AVI file doesn't get closed properly in the software and it shows up as a corrupted file. I think it's rare, and I think it just ends up having issues being opened in certain software, but not all. But yeah, this would be maybe another reason to not save everything for one file in case there's a crash that corrupts the file. But I think that's really rare. Yeah, and it should be pretty much always up to date within a frame or two.
Good to know.